Okay, so picking up where we left off yesterday, I am going to tell you that today is going to be a tiny bit confusing. I'm going to try to correct some things that we did earlier in the class today to see if that helps y'all understand this. So using the method that I just showed you about how to estimate a pH, we're going to figure out which one would make the best buffered system. Something that I haven't shown you yet that I'm fixing to tell you that you can use for this problem is that the pH is equal to the pKa. So when we want to pick a plus or minus 1, we want to pick a buffer here, or the acid that's going to be closest to the pH. So just do pH is equal to pKa to get which one of these is going to be close to the buffer that we need. Okay, it'll make more sense in a minute. So using that method I just showed you, because this is multiple choice, let's not use our calculator and let's estimate what we think the pKa's are going to be here. There's two we can throw out right away, just based on that. What two can we throw away right away? A, get rid of it, it's going to be 2 and D. Okay, so that's going to leave us with B and C. So if we do our estimated pH, which one of those would be closest to 4.3? We do our pKa of those. Yeah, C. Okay, so C would be the answer. Okay, because when you actually calculate them, this one comes out to 4.89, this one comes out to 4.19. So that one is definitely closest to the 4.3. So we would use benzoic acid. Then it says calculate the ratio of acid-base required for each system to yield a pH of 4.30. Then it says which system works best. Well, we just skipped to it and said, hey, we don't need to do all those other ones because we can just go to benzoic acid. So we have, because we have a pH right here, we can calculate our hydrogen concentration. Do you agree? 10 to the negative 4.3. Okay, so it is telling us to calculate that. So if we throw that in the calculator, we get 5 times 10 to the negative fifth. And then using our handy-dandy formula of H plus is equal to Ka acid-base ratio, we can solve for our acid-base ratio. So that would be H plus equals Ka. So 5 times 10 to the negative fifth over 6.4 times 10 to the negative 8. No, where did I get that from? Negative 5. Guess what happens here? What can I cross out? So there's my ratio, right? 5 to 6.4. So 5 moles of acid to 6.4 moles of base. Or if you wanted to do a calculation, you could do 0.78, but that doesn't really help us. So that's the ratio of how we would work that. So you need 5 parts acid to 6.4 parts base to make this buffer. Okay. I just canceled out the times 10 to the negative 5 because it's on the top and the bottom. Yes? Oh, I meant 6.4. I don't know why I did double colon. I like colons. Wait. Just okay. All right. So that's going to bring us to acid-base titration curves. One of the worksheets you pick up today said demystifying the titration curve. It's not a worksheet. It's actually a video that I want you to watch. It is in the acid-base unit. It's down at the bottom. I have the code on there. It's Linus Pauling, all one word, lowercase. It is an older video by Renee McCormick, who is like the guru of AP Chem and NIMSI, National Math and Science Institute. It's a very good video, okay? She's a little wordy, even more so than me, if you can believe that. But she is a very excellent teacher, and so that curve, Paige still remembers that video as helping her. Like, she's like, yeah, tell them they need to watch that. So Paige says you need to watch it, okay? Okay. So when we're doing acid-base titration curves, it's going to depend on whether we're doing strong or a weak strong. If we're doing strong, then it's just stoichiometry problem, okay? If we're doing weak strong, then we got to do some Rice tables, our magic equation, some stoichiometry. It's a lot more complicated. So if you see that they're asking you questions about a strong acid, strong base titration, be very happy on the inside because it's way easier, okay? If I'm doing a titration curve and it's strong, then my equivalence point is 7. But if I'm not strong, if I'm weak strong, you're going to either be above equivalence point of 7 or below, depending on which one is your strong. So if I have a weak acid and a strong base, my equivalence point will be higher than a pH of 7. If I have a strong acid with a weak base, my equivalence point will be less than 7. Okay? And I know on yours it's a funny looking arrow that whenever it converted from PDF to Word, it does some crazy things with the symbols. Okay? There is a distinction between an endpoint and equivalence point. Okay? The endpoint is where the color changes. Like if I'm doing a manual titration and I put an indicator in there, that's where the color changes. The equivalence point is where it is actually equal moles of hydrogen to hydroxide. That's what makes it a neutralization reaction. I have neutralized and they have an equal concentration because they react in a 1-to-1 ratio to form water. Okay? So the equivalence point is where hydrogen and hydroxide are exactly equal. Okay? That's important. That's the same whether I'm doing strong and weak and weak and weak. It's always the equal amounts of hydrogen and hydroxide. Okay, so here we're going to do this one. This is a strong, so this one is a happy dance. Okay, but before we go into this, because this is something that tripped them up earlier, so I want to show you this real quick so that we don't get confused. I'm going to be using something called millimoles. Okay, because it makes our math easier. Because we can subtract with whole numbers, which are better and easier than decimals. Okay, so what do you think a millimole is? 1,000 moles. Okay, so what I can do, if I take a molarity, let's just show you this. If I take a molarity and I have 0.20 moles per liter, and I want to turn that into millimoles per milliliter, what am I doing to both parts of the equation? 1,000, right? Millimoles is equal to 1 mole, and then 1 liter is equal to 1,000 milliliters. Cancel, cancel, cancel. So 0.20 millimoles per milliliter. Does that make sense?
Wait, 0.2 or 2?
It's 1,000 of a mole.
You'll see why it's better. Okay, because now if I multiply by volume, let's just go with 50 mils since that's our problem, times 50 milliliters, cancel, cancel. I have how many? Say it. 10 millimoles. It's much easier to subtract something from 10 than 0.01. So that really threw them today, so I wanted to show you where I'm getting that from so you don't get confused. Because then they got kind of stuck on that and it made it more confusing. Okay, so you get where the millimoles are coming from, right? Okay. Then let's clear that, erase, and get rid of that. Okay. So, in the beginning, I have 2 A's for some reason. Okay, says I have titration between 50 milliliters of HNO3 and 0.1 molar of NaOH. So right off the bat, before I do anything, we just did this in the last slide, you understand that I have 10 millimoles of hydrogen, right? Do you understand that?
Yes.
Thank you. I need confirmation. Okay. Okay. So your A on your paper, I think it says no NOH has been added, right?
Mm-hmm. Yes.
Okay. So guess what? Negative log of 0.2 molar, because that's the concentration of hydrogen in the beginning, gives me a pH of 0.699. It's a strong acid. I can take straight from the concentration. Why did I do 3 decimal places? Because I had 3 significant figures in my concentration. So that's part A. Okay? So for 10 milliliters of hydroxide added for part B, right, I know that my neutralization reaction is a 1-to-1 reaction, correct?
Yes.
Right? I make water. Okay, I know that I have 10 millimoles here. Okay, I just added 10 milliliters of 0.1 molar. If I change that to millimoles, how many millimoles of hydroxide do I have? 1. Because 10 times 0.1 is 1. So I have 1 millimole here. Those are going to react, right? Volume times molarity is giving me millimoles. I just changed it all to millimoles because it's much easier to subtract 10 minus 1, okay, than 0.001 minus point whatever, okay? That's all I'm doing is making my math easier. So then I'm going to subtract 1 and 1. That's going to leave me 9 millimoles of hydrogen, 0 millimoles of hydroxide because I just consumed it, right? So now to get the pH, what do I need?
-1 concentration.
I need the concentration first though, right?
Yes.
Right now I have millimoles. So I got to get my concentration. So I have 9 millimoles over what's my new volume?
60.
60. Because I had the original 50 mils of acid and I added 10 mils. So now I can divide by 60 milliliters and that's going to give me 0.15 is my concentration. So if I take the negative log of that, my pH is 0.824. I need to know that you understood why I did that part.
No.
It's a rice table, right? Because if I'm adding, what happens when I add a base to an acid? They react and they neutralize each other. I've only added 1 millimole of hydroxide right now, so it's going to react with what I have of hydroxide. So I'm going to consume all of my hydroxide, it's going to be gone, and then I'm going to have some leftover acid. My leftover acid is like my excess reactant, right? My 1 mole or 1 millimole of hydroxide is like my limiting reactant. I'm done. I don't have any more of it. Okay? Yes.
So can you go through how you got the 1 millimole of hydroxide?
10 times 0.1,
And you multiply by 10 because...
because that's the volume I added. It says right here I added 10 milliliters.
Oh, okay.
It says I added 10 milliliters of 0.1 molar. So I did 10 times 0.1 gives me 1 millimole. When I do milliliters times my concentration, it's a millimole. Because I'm assuming that I made my concentration as millimoles per milliliter, which is the same number, right? Because it's 1,000 on the top, 1,000 on the bottom. Okay? So now let's do that again for part C. I'm going to erase all this. Is it bothering you to write on top the words? Because I can put a blank page. Okay, erasing. So now we're doing this one, 20 milliliters. Okay, so if I have 20 milliliters, right, part B is 20 milliliters of hydroxide, right? So 20 times 0.1, my OH now is 2 millimoles, right? Because these are total volumes not adding. So now for my total volume of 20. So I go back to my H plus OH yields water. Still started with 10 millimoles here. Now I have 2 millimoles when I added 20. So I'm going to subtract minus 2 minus 2. That gives me 0. That gives me 8 millimoles of hydrogen. So to get my pH, I need to convert that back to concentration. So what is my new volume now?
20. Or 70.
70.
50.
Yeah, they're additive. 70 milliliters, which is going to give me 0.114 molar. So then I'm going to take the negative log of 0.114, and I'm going to get 0.942 is my pH. Guess what it would be if I added 30 milliliters? I would be subtracting 3 from 10. You see what I'm doing here? Okay? before I erase, does everybody have this?
So you're subtracting by 2 because you want to get rid of the hydroxide.
Well, I am. The hydroxide is reacting. It's not that I'm getting rid of it.
Yeah,
It's reacting with the original amount of acid that was there. So two millimoles reacted and neutralized. So now it made water. Okay, that leaves behind 8 millimoles. I still have 8 like excess reactant.
Okay.
Okay, all right. Okay, I'm erasing. Now I'm going to do the next one. So now we're doing this one. Okay, so now I have 50 milliliters of acid, of hydroxide being added. So, I mean, the down and dirty way is 10 minus 5, right? But I'll write it out. So H plus OH, making water. Still had 10 because I haven't changed that. Now if I do 50 times 0.1, I get 5 millimoles. So this is 5, minus 5, minus 5. This is 0. Now I still have 5 millimoles of acid. I should expect my pH to go up here, right? I have less of it. Now what's my new volume? 100. 50 plus 50. So 100 milliliters. And that's going to give me 0.05 molar. I take the negative log of that, and I get 1.301 is my pH. Okay? So now let's do 100 milliliters. All right? Erasing. So now we're doing this step. So H plus, still 10 millimoles. OH. What is 100 times 0.1? 10 millimoles. I have the same amount of hydroxide, minus 10, 0, 0. So my hydroxide and my hydrogen are equal. What does that mean I have reached? Not equilibrium. Equivalence point. That means my pH is 7. Because I'm a strong acid and a strong base, and that makes a pH of 7.
Oh, so when we're minusing the one that has the least amount of millimoles, right?
Well, yes, because we'll run out of that first. It's limiting. We're running out of that.
Okay.
Yeah. Okay? Now what happens if we go past our equivalence point?
Basic.
It's going to be basic. Should we have any hydrogen? No. But now it's going to look a little bit opposite. So we're still going to throw this H plus OH minus. I'm not doing the water. You already know that, Sarah. This is still 10 millimoles, right? Because we're not doing additive volumes. We're doing total volumes. What would the pH be? So now I have 200 milliliters times 0.1. So how many millimoles of hydroxide do I have? 20. So now we're going to run out of hydrogen. So I'm going to do minus 10 and minus 10. So I'm going to give me 0 for hydrogen and 10 millimoles for hydroxide. What's my total volume now?
250.
I just made hydroxide positive. What the heck am I doing? So now I'm going to divide that by 250 milliliters, and I'm going to get a concentration of 0.04 molar hydroxide. So now I'm going to take the negative log of 0.04, and I will get 1.39, which is my pOH. So that means my pH is 12.61. And that's my answer there. Okay? Well, I would say I have good news, bad news, but I really just have bad news for you. That's the easier one, because it's all just stoichiometry subtracting. Okay? Weak acid, weak bases, not so much. It's a little bit more difficult. We got to do 3 different things. Okay? Not 3 different things. Actually, more than that. I highly recommend you watch that titration curve video. the demystifying titration curves. It will make a big difference in this unit, I promise. And if you're feeling dazed and confused, you're joining the rest of the AP Chem students across America. This is typically the most, I don't know if difficult unit is, it just, like wrapping your brain around it is just hard. There's lots of whining and crying and gnashing of teeth. Okay, so let's talk about the titration curve and the points along the way. Okay, get rid of that. All right, so when we're talking about these points along the titration curve, we're referring to either a weak acid with a strong base or a weak base with a strong acid. Okay, so number one, the pH before the titration begins is a rice table, just like what we've been doing to get that. Okay, we haven't created a buffer or anything like that. We're just going to do a rice table that's in order. So our regular rice table, where we're going to do the Ka ends up being equal to x squared over concentration. Okay, assuming that you neglect the x like we've been doing. Okay, so that part is the same. When we get to, as soon as we add even one little tiny drop of what we're titrating with, we now have a buffer. Because as soon as we add one of the base or the acid, whichever we're titrating with, we are now creating the conjugate. So we have created a buffer. And so when we look at these titration curves for weak acids and strong bases or vice versa, you're going to have when you first start doing it, your pH is going to be fairly flat. And it's going to keep kind of going fairly flat, and all of a sudden it's going to shoot up. Okay? And where it's going fairly flat is the land of the buffer. Okay? Which is where you're going to use the HA is equal to Ka acid concentration over base. Or the Henderson-Hasselbalch equation if you like that one. Okay? Either one of those works there. Okay? And so whatever it is, you're going to make sure you have to calculate new concentrations though, right? Because once I have an acid and I add some base along with some volume, I got to have to calculate new concentrations. Okay? Just like what we did yesterday. We calculated new concentrations once we added some stuff in there. Okay? When you get to the half equivalence point, okay, this is very important. I want you to circle it, star it, whatever. At the half equivalence point, your pH is equal to your pKa. The half equivalence point, literally, when you're looking at that flat line space, is right smack in the middle of it. That's your half equivalence point. At that point, you have an equal concentration of acid and conjugate. Before the half equivalence point, you have more acid than conjugate. At the half equivalence, they're equal. Afterwards, you have more conjugate than acid until you run out of acid. Okay? That'll all be explained in that titration curve. But pH is equal to pKa at the half equivalence point. That's all you have to do is take the negative log of your Ka value, and that's your pH. Okay? You can do it with the calculation, like more complicated, but why would you? Because you can just go, oh, I've got a Ka value, I can take the negative log, and that's my pH. Only at that half equivalence point. At the equivalence point, you are simply calculating the pH of a salt, which we did yesterday, right? Or the day before, where we said, hey, if I know my Ka and I have a basic salt, I can figure out my Kb of my salt, put it in my rice table, and then it's equal to x squared over concentration, just like before. So none of these steps are new. We just got to put them together and know when to use them. And then the last step is when I go beyond the equivalence point, okay? And that's going to be the calculating of whatever you have excess. So it's either going to be excess hydroxide or excess hydrogen, depending on which way you're titrating. And that should be straightforward. Just remember to do molarity, not moles. Okay? All right. Here we go. We're going to talk about how to write that hydrolysis of the salt, because we need that to put in our rice table when we get at the equivalence point. Okay? There's a lot of words. You can go back and read them. I'm going to show you the quick and easy way to do it. Okay? Using these examples. Okay? You are going to take, when you look at your salt, you're going to take whatever came from the weak, and you're going to add it to water and see what it can do. Okay? For instance, A is potassium nitrite. So the two things that it came from are KOH and HNO2. KOH is a group 1 base. It's strong. We're not going to do anything with that. So we're going to take the part of that salt that came from the weak acid, which is the NO2, and we're going to add it to water. It sometimes helps to write water as HOH, so you can see how it splits up. So the only thing that that NO2 can do here is what? Accept or donate a hydrogen? Accept. So it accepts a hydrogen, which makes it a... What accepts the hydrogen? Base. And the water donates the hydrogen, which makes it an acid. So what's left is a strong hydroxide, and it reforms HNO2, which is a weak acid. So that means when we did a rice table on this for this basic salt, we would be calculating an OH concentration, taking the negative log, and then subtracting from 14. Okay? If we look at part B, it's the same concept, but now we're doing an acidic salt, because I come from NH3 and HNO3. HNO3, strong acid, we don't care about it. So we're going to take the weak part of the base, in this case it's the NH4, we're going to add it to water and see what it can do. Well, I've never heard of NH5, have you? No. Okay, so it's going to donate a hydrogen from NH4 plus and leave behind on the other side this would be the same thing as H3O plus, if that helps you, from the water. And so then if I did this one, when I calculated my X value, it would be for an acid, and I could go straight into my negative log and be done. Okay? All right. Take a deep breath. Are you ready? Here we go. Here we go. All right. This is asking us to calculate the pH at these points of a titration. Okay? We have hydrogen cyanide gas and sodium hydroxide. So we have a weak acid with a strong base. Luckily it's not even asking us to calculate it beforehand. But if we were to calculate it beforehand, we would do the Ka is equal to x squared over concentration, and we could figure out what our value was before. So it's asking us at 8 mils of 0.1 molar have been added. Okay, so we are not to the halfway point yet. So we're going to use our calculate this equation. H plus equals Ka and then acid over base concentration. Okay, but we've already added some stuff, so we can't use the concentration that's in the problem, right? Because they've already been doing some neutralization. Okay, so we're going to calculate our new concentration of A. Ready? I have to take volume times molarity of my acid. So 50 milliliters times 0.1, which ends up being 5 up here, okay, minus how much base I added, right? We saw that from the problem before. We have to subtract out the base because it's going to react. Okay, so it's going to neutralize that little tiny part of the hydrogen. So then I'm going to say 8 milliliters times 0.1 molar. Then I'm going to divide by my new volume. What is my new volume? 58. That ends up being 0.072. Now I need to do the same thing and calculate my new concentration of base. Right? This is 0 because I had none, right? Say yes, I had none. Okay. Plus, because I'm adding some, 8 times 0.1 molar. Divided by 58. which ends up being 0.013 molar. Before I move on, what? Yes,
Okay, why are you subtracting on the top?
because it's neutralizing.
So, because 8 moles.
Acid is base, so it has to so this ends up being 0.8. So 0.8 millimoles is going to react with 0.8 millimoles of the acid, leaving behind 4.2 millimoles,
Okay, that makes sense.
right?
Yes.
Okay. But then for the base, for the new concentration, I don't have any base to begin with. I added some base, but I have a new volume.
Okay. And
Okay.
so the base hasn't been neutralized, but some of the acid.
Well, I have to know what the concentration of it is for B to be able to do the calculation.
Okay.
Okay, so now I'm going to go plug it all in. My Ka value was 6.2 times 10 to the negative 10, right? Equals, not equals, sorry. H concentration is equal. So then I've got 0.072 over 0.013. So when I do that math, I get 3.25 times 10 to the negative 9. Huh? What?
Is this part A?
It's all part
Is
A,
this
right?
part A?
This is all part A. This is all part A. Yes.
Why is the concentration of hydrogen ions not just the concentration of HCN?
Because it's a weak acid.
Okay.
Yeah.
That's what I thought.
You can only do hydrogen concentration of the direct concentration of your acid when it's a strong acid. So now I'm going to take the negative log of 3.25 times 10 to the negative 9, and that gives me a pH of 8.489. Okay? So that's part A. Who's ready for part B? I promise you part B's easier. The concentrations of A and B are not equal to each other.
Oh, the moles are.
The moles are, but the concentrations are not. That's the hit right there. The moles are equal, but not the concentration.
How do they have the same moles? Do they not have the same volume?
No, the moles are not equal here. I'm sorry, the moles are not. The only time the moles are equal is at equivalent points.
Oh, I was talking about
Yeah.
B, that's why.
But B is not the same. It's different.
Oh.
Okay. All right. You ready for part B? It's way easier. Erase. Okay. Part B says at the halfway point of this titration, which means half equivalence point, which means pH is equal to pKa, which means negative log of the Ka value. That is nice. And it's nice that they told you it was the halfway equivalence point. If they didn't gave you some numbers, sometimes you have to figure out, oh, that's the half equivalence point. pH is equal to pKa.
What are some other indicators of the halfway equivalent?
The graph, if you're looking at the graph.
The graph. Okay.
So when you're looking at the graph, if you find the halfway equivalence points, you can bring it down, figure out what pH is, then that's equal to pKa, and then get your Ka value.
Okay.
Bam.
That's the only way you would figure out if it's at.
No, based on numbers, like if they said, hey, this many moles, and you have to do the stoichiometry. Okay, let's do the last step. It's not as easy as the second step. Okay. All right. Erase. All right, now we're doing C. I'm going to start up here because it's going to take some work. Okay. So at the equivalence point, if you go back to what I told you, at the equivalence point, you're dealing with the salt. Because at the equivalence point, your hydrogen concentration is equal to your hydroxide at this point for just straight up that. But we're dealing with the salt. So we have a strong base and a weak acid. So do we have, what kind of salt do we have? a basic salt. Okay? So first thing we want to do is make sure we know how to write our reaction. So that we know we are going to be calculating ultimately a hydroxide concentration when we get done with this. Okay? We have to calculate what's the concentration of CN minus. Okay? So, I ask you this question. How many millimoles of base do we need to react with the acid? So, how many millimoles of acid did we begin with? So we have, in the beginning, we had 5 millimoles of hydrogen, right? So that means we need 5 millimoles of hydroxide, right? If they're one-to-one reaction, we're equivalents, they've got to be equal, okay? So if we need 5 millimoles of hydroxide, how many millimoles of cyanide do we have here? 5 millimoles of cyanide. What is my new volume with all this going down?
We don't know.
How do you not know? You got 0.1 molar. How many milliliters would give you 0.1 molar?
5.
50 milliliters. But I have 50 milliliters of acid, and I have 50 milliliters of base, so I have 100 milliliters, which gives me a concentration of 0.05 molar. Yeah?
That's hydroxide, right?
Nope, that's the CN.
Oh, okay.
Wait.
That's CN minus. So now I have a salt, I have a Ka value, but what do I need? Because I need to do Kb is equal to hydroxide, HCN, right? Over CN minus, right?
Wait, why can't we use Kb equals Kw over Ka?
That is exactly what we're going to use.
Oh.
But I'm showing you why we need a Kb,
Oh, okay.
right? So we're going to find Kb by doing Kw over Ka, which is going to be equal to x squared over 0.5, right? Minus x, but we're neglecting. Yeah?
Is it 0.5 or 0.5?
Right here, I got the 0.5 right there.
0.05.
Oh, I transposed my numbers. Whatever that's called, I do it a lot. Where I I write down the opposite of what I have. Like 45, I write down 54.
Just calculate.
Yeah, I have that. Bad.
It's like math percent stuff.
It is, exactly. Also, when I'm doing a lot of like talking, writing, and copying down, it happens. Okay, because right now I'm more focused on getting you to understand what I'm doing than the number. Okay? All right, so do you know what I've done so far? 50 plus 50. 50 is from the acid, 50 is from the base. Because in order to get 5 millimoles of hydroxide, I had to use 50 mils to get it. Yeah, so this is what makes AP difficult. They didn't tell you any of that. You had to figure it out, right? We had to figure out, okay, I need 5 millimoles of base, so how much volume would give me that? And it was 50. So then I add that to my new volume. Yes, because I need to neutralize 5 millimoles of the acid.
Yes, and then, okay, but then how do you go from that millimole to millimole?
Because I have my molarity of my base, which is 0.1.
Okay.
So what times 0.1 would give me 5, and it's 50. Yeah. Okay. All right, so now, are you ready? Woo-wee. Here we go. So I'm going to have 1 times 10 to the 14, negative 14, over 6.2 times 10 to the negative 10 equals x squared over 0.5. Oh, 0.05. Dang it. Okay? I'm just doing it all in one step because I'm handy with the calculator. And so are you. So when I get this, x is going to be equal to 8.98 times 10 to the negative 4, which is my hydroxide concentration, right? I'm going to take the negative log of that, and I will get that my pOH is equal to 3.047. So what is my pH? 14 minus that, 10.953 if I didn't transpose any numbers. Questions?
So many.
So many. Yeah, this is usually one of the toughest lessons.
Wait, why is it HCN on the bottom? I mean, why is it CN minus on the bottom?
Products over reactants, dear.
Products over. Oh, and it's the big equation on. Okay.
This right here, this is products over reactants for KB.
That's products over
Can
reaction.
you walk through how you you know they're like H plus and 5 millimoles, you need 5 millimoles.
Okay, so the question is, could I walk through how that I need 5 millimoles? So from the very beginning, right, I do my concentration of my hydrogen in my acid, 5 millimoles, okay? I did that by doing 50 times 0.1. That's 5 millimoles. That's my total amount of hydrogen throughout the whole experiment, okay? In order to neutralize 5 millimoles of hydrogen, I have to have 5 millimoles of hydroxide. They have to be the same because we're at the equivalence point, okay? So then I said, okay, if I need 5 millimoles of hydroxide, right, I have 0.1 molar hydroxide. What times 0.1 will give me 5, and it's 50. So I add that 50 mils to the 50 mils of the acid for a total of 100 milliliters, right? If I have 5 millimoles of H, I also have 5 millimoles of CN, right, when they break up, okay? So then I got the new concentration of CN at the equivalence point. It is not the same as the concentration of the hydroxide because now I'm reacting that.
I meant H plus.
It's, well, not at this point because I have no more H plus at this point because I consumed it all. So it's, yeah, so it's consumed, okay? So then I plug it in because when you are at equivalence point, you're finding the pH of your salt, which we did yesterday, right? We found pHs of salts yesterday, okay? Because what's left is the conjugate from the acid will react with the water to form hydroxide. That's why it's a basic salt. So then I have to do the whole, I got a Ka value, I got to find a Kb value, and it's always equal to 1 times 10 to the negative 14. So this, what we did, this is just like the problem we did yesterday. We're just now putting all of those problems in a titration now. And you got to know when to do what problem at what point in the titration, which is why this is the unit from Hades.
So like the point C, there was like a multi-part. Like the first one, you need to figure out how much CN you needed.
And what first part?
Or like, because in the step that you did to solve C, because there were multiple steps, it wasn't all.
Mm-hmm.
So the first part was figuring out, what is so funny?
It's his.
Oh my god. Is the CN concentration, and then you found out.
Then I just plugged it in over here to my Kb expression.
Okay.
That's all it is. This would be 0.05 here. Normally it would be 0.05 minus x, but we are assuming with this really small Kb values that we can neglect.
You found the concentration.
And they would not give you one like this that you could not neglect because the math would become a nightmare. Okay? We have like 2 more slides to get through very quickly. Okay? Hopefully. Okay? Okay, So that's going to take us to acid-base indicators. Endpoint, remember, is where the indicator changes colors. If you are asked to choose an indicator, we want to choose an indicator that has the equivalence point as close as possible to our pH that we're targeting. Okay, strong acids, strong bases have a large vertical, so you can use a lot of different indicators. We typically use phenolphthalein, but usually indicators are weak acids. They have one color in their acidic form, one in their basic form. Okay, the useful range is pKa plus or minus 1. So that's what you want to circle there. So you find your indicator that they're showing. It'll have a Ka value. You do the pKa of plus or minus 1, and that's going to be a useful range for your pH. Okay, so you're going to choose that based on that. Okay, so in this case, your chart's not in your notes. It says use table 15.8, but I put this table in there. So if we were going to do the titration of ammonia with hydrochloric acid, so we have a weak base with a strong acid, where is our pH equivalent going to be? Below or above 7? Below the strong acid. Okay, so we're going to be looking at not 7, we're going to be looking at slightly below 7. So which one of those would probably be the best choice? Methyl red. Methyl red would be the first choice. Best choice. If I was going to do a strong base with a weak acid, which would probably be the better one? No, that's too high.
Thymal blue.
Thymal blue would be a better choice. That's how that works. Okay?
When would you use something like AY? Like alizarin yellow?
It would have to be like if I was actually trying to find the pH of something without a titration. Like if I had this stuff and I say, I wonder what this pH is, I could use that to an indicator, and if it was going to be the bright yellow, or the violet, if I had something, if I wanted to know if it was an acid or a base, and then litmus paper just does red or blue, right? Okay, but if I wanted to further identify how low my pH is, I could use some of these indicators for that. That's a good question. And then the last one is that bromethymol blue has a Ka value of 1 times 10 to the negative 7. It's yellow in its acid form and blue in its conjugate form. Suppose we put a few drops in an acid solution and then we titrate it. At what pH will the indicator first change color?
Wait,
Y'all tell me?
pKa equals 7.
The pKa is 7, right, because of that. And what did I tell you?
pKa equals pH.
Plus or minus 1.
So between 6 and 8 is when that would change. That's how you do that.
That's as close as you can get. You just say between 6 and 8.
And honestly, bromethymol blue is what we used when we did our titration in Chem 1. And green is the magic point. If you're at 7, you're like green. Okay? All right, I'm going to...
And you give it a starburst.
Do
Yeah,
yeah.
you get a starburst and